Hello, everyone. I have the pleasure of working with Achyutan this summer and introducing him now. He's a rising junior in Portland, Oregon, and this summer we've worked on understanding and modeling dengue occurrence across the southern U.S. and the Caribbean, and he's going to talk more about that. Um, thanks.
Okay, yeah, I'll share my screen right now. Okay, you guys can see my window, right? Okay, all right, all right. So good afternoon, everyone. I am Ashtan Veeraraghavan, and me and my mentor, Dr. Anthony Campbell, have been working on a project which we were mapping vector-borne diseases using Earth observation, spatial data, statistical analysis, as well as AI and machine learning. We were mostly focusing on dengue for this project. So. First off, I want to address in case anyone doesn't know what dengue actually is. So dengue is basically a rapidly spreading mosquito-borne
Your
disease.
slides yet are not showing yet.
Yeah, I can't see the
Wait,
slides
what?
yet.
You
Sorry.
can't see the slides? Hold
So
on.
it says
Wait,
loading.
it says it's paused. Hold on.
And Sam can share them if there's any issue.
Hmm. Okay.
Sam, why don't you share them?
Yeah. It seems to be paused.
Well, it's not the first time. That's why we always have a backup plan.
Hmm.
So hopefully Sam can find your slides. All right.
Okay.
Perfect.
Okay.
That's what we're looking
All
for.
right.
Okay, take it away, Ashita.
All right. Starting again. Good afternoon, guys. I am Ashtan Veeraraghavan, and me and my mentor, Dr. Anthony Campbell, have been working on a project in which we have been mapping vector-borne diseases using Earth observation, spatial data, statistical analysis, and AI and machine learning. Next slide, please. Now, first of all, I would like to address to you guys in case you guys do not know what exactly dengue is. Dengue is basically a rapidly spreading disease caused by the mosquito species called Aedes aegypti. It's the main vector in this disease. It can be caused by four viruses that each can range from severe fever to near deadly symptoms like joint pain. And even though it cannot be spread through human contact, there are still over 400 million cases throughout the world. And they're more prevalent in urban regions like
Ashitan, we can't hear you anymore.
tropical. What?
His internet connection froze.
Ashitan, why don't you turn your video off?
Okay. Can you guys hear me now?
Yes.
Okay. Can you guys move on to the next slide, please? Yeah, thank you. Now, some factors that influence dengue, there are certain climate-related factors like temperature, rainfall, precipitation, and humidity. The higher each of those are, the better breeding grounds it can cause for Aedes aegypti species, thereby increasing the risk of spreading dengue. There are also environment-related factors like altitude, freshwater, and vegetation, which can also influence the breeding areas and ability for the mosquitoes. And there are also human-related factors like urbanization, socioeconomic status, and population density. In different ways, each of these three can impact and increase human mosquito contact, which also increases the risk of dengue transmission. So now diving into our project. The goal of our project mainly was to create a model that can predict dengue occurrence based on different factors like GDP, nighttime lights, population, and other environmental and human-based factors. We mostly focused on southeastern USA and Puerto Rico, and we also utilized machine learning to fill certain gaps in our data, such as GDP. And we also use Google Earth Engine in order to run this project through remote sensing and spatial analysis. My main goal for this project, personally, was to learn skills for remote sensing and spatial analysis and conduct a successful spatial analysis with health data. So what we got done so far is firstly, we visualized data from original CDC reports on dengue and on the USA, and also we did reports on GDP by county through Google Colab. And after that, we analyzed map data on Google Earth Engine, and using that, we ran species distribution models for habitat suitability for Aedes aegypti. After that, we predicted GDP by county for Puerto Rico using some certain machine learning models trained for GDP by US counties. And we used the other environmental and human-based factors to model dengue occurrence in 2022 and apply the Shapley value approach to each of the models. So for our GDP prediction for Puerto Rico, after we ran the 4 models, which were linear regression, random forest, SVM, and XGBoost, we found that random forest was easily the top performing model with the highest accuracy or R-squared value and the lowest errors like mean absolute error, absolute percentage error, and mean squared error. Linear regression was the polar opposite, being completely outperformed in every aspect, while XGBoost and SVM were somewhat in between, nearly as good as random forest, but not as high of an accuracy or low error rates. Next slide, please. Now moving on to our species distribution modeling. So originally, I tried to run species distribution models for all of the Americas, North and South America. So I had to merge 12 separate models to get around slow computing times. But because of the way the pseudo absence data was created, it created a very unclear map with clear overlaps. So instead, I decided to focus on one region in the Gulf of Mexico and the Caribbean Sea, which demonstrated a seamless map with better pseudo absences and more data to accurately train our model. Now moving on to our Shapley analysis, in which we found our top 5 important features for each of the travel-associated and the locally acquired cases, which included GDP, precipitation, and nighttime lights, as well as the species distribution models for travel-associated cases, and land surface temperature, and also some more nighttime light statistics, and the species distribution models for locally acquired cases. After that, I found some plots and which compared the Shapley values with the county data for each important feature. So for example, GDP in 2022 for travel cases. So the Shapley values, as the Shapley values increase, it is directly related to the risk of dengue spread. So in this plot, as GDP for 2022 increases, the risk also increases for travel-associated cases because counties with higher GDP have higher populations and economic activity and thus are more likely to travel. Meanwhile, land surface temperatures for localized cases impact the breeding grounds for Aedes aegypti, which is also directly related to dengue risk. For travel cases and localized cases for the SDM mean, which is habitat suitability, travel cases have a lot more linear relationship than the SDM mean because the localized cases because they have negative Shapley values, mostly negative Shapley values due to certain behavioral actions or which the lower mid-range values tend to lean more towards lower risk than higher risk compared to the travel associated cases because of a context dependent effect. Next slide, please. From this experiment, we can then conclude that GDP, land surface temperature, nighttime lights, habitat suitability, and precipitation were all crucial drivers of dengue occurrence in 2022. And from the Shapley value analysis, in addition to each of the GDP, land surface temperatures, and habitat suitability, precipitation, while not shown, also had an interesting effect. High precipitation in September and April increased the risk for travel-related cases, demonstrating the possibility that our model can pick up travel-related behaviors from some people during their travel, like traveling to tropical locations when their home county was rainy, thereby increasing their risk of getting dengue at their home county. Now for our future editions. So a couple things I'm going to add for the future are using our species distribution models and our predictions to create an app on Google Earth Engine that visualizes our outputs to show and make it accessible to anyone who is willing to see the data. After that, I'm planning on making a research paper to publish this data because other current research papers are lacking information regarding factors like GDP, nighttime lights, and stuff. I also could have focused on more of an outbreak year, like 2013, for example, because that had more cases than the year I worked with, 2022, in which we could have had better predictions because of the extra data. And the roadblocks I encountered were even running the code and running the SDMs, which are expected, and that's because it's mostly part of the process. And if not for those, I probably would not have gotten as far as I did.
All right, we're almost at 11 minutes. I'm sorry to cut you off.
Okay.
Do you have a final thought?
Yeah. I would like to end by thanking my mentor, Dr. Anthony Campbell, for helping me with this entire project, with his knowledge and his expertise, and helping him and his teaching on remote sensing and spatial analysis. And I believe without him, I would not have been able to get this project done. So I'd like to thank him for that. And that's all from me.
Thank you so much, Ashutan. Does anyone have a quick question? Just one, if possible, or we can let Ash, it's very late where Ashutan is, so we can let him
That
listen.
was a great talk and very interesting results. We've never really had a project about dengue before, so it's very interesting to see the results and also to learn a little bit more about machine learning models because
Yeah.
that's something I've been trying to learn about. So I think that probably was very fun for you.
It was. Yeah, thank you so much for giving me this opportunity. And yeah, it's been a really fun topic for me to present, and which is why I got into this project in the first place.
All right. Well, very well done.
Yeah, excellent.
Does anyone else have any questions or anything?
All right, let's move on. And Ashutan, thank you so much for staying awake. And now you can go to bed.